In the last video, we showed that a matrix is invertible if and only if you can find a sequence of row operations which convert that matrix into the identity. We're now going to develop that into a method for actually computing the inverse of an invertible matrix. So let's say we have a matrix A and we want to find its inverse if it exists. The method goes as follows. We start off by forming the super-augmented matrix A followed by the identity. So the reason I'm calling this the super-augmented matrix is because usually when you've got an augmented matrix you add one extra column, but here we're adding n extra columns. So for example, if A was equal to 1, 2, 3, 4, then the super-augmented matrix A followed by I2 would be 1, 2, 3, 4, and then the 2 by 2 identity like this. So we then do row operations to put this super-augmented matrix into row-reduced echelon form. Then at step 3, if the result of doing that is the identity and then some other matrix B on its right, then our original matrix A is invertible and B is its inverse. So I'll explain why B is its inverse in a moment, but the reason that that shows A is invertible is because you've done a sequence of row operations to A and ended up with the identity, so the theorem we proved last time guarantees that A is invertible in this case. So finally, if the first part of the matrix A is not the identity, then A is not invertible, again because the first part of the matrix will be the row-reduced echelon form of A, and if that's not the identity, then we know A is not invertible. So let's go on to this part 3. Let's go back to there and say, why is this true? So why does this work? Why is it that the B part of this matrix is actually going to be the inverse of our original matrix A? So we've done a sequence of row ops, so let's give notation for those. So let's let R1 be the first row op you did, and up to RK be the row ops. And corresponding to those row ops, we have elementary matrices. So we're going to let EI be the elementary matrix RI done to the identity. So doing these row ops was the same as left multiplying by the elementary matrix EI. So what we have is that when we do these row ops to the initial matrix A and then the identity, we get, well, you'll have EK minus 1 down to E1 multiplied into A, and then you'll also have EK down to E1 multiplied into the identity, which is of course just EK down to E1. All right. So if we give the name E to this product of the elementary matrices, then this is EA on the left and E on the right. Okay, but it's also equal to something else. So we have EA and then E, that is the identity, and then B, because we're assuming at part 3 that we got the identity and then B. So this B is actually the product of the elementary matrices, which we're calling E. So in particular, EA is equal to the identity. And remember, that tells us that A is invertible because we have done some row operations to A and got the identity matrix. And if you multiply on the right by A inverse, then A inverse is equal to E, which of course, as we've just seen, is equal to B. Okay, so that's why B is the inverse of A when step 3 actually holds. Okay, so that's our method for finding inverses of invertible matrices, and in fact for determining in general whether or not a square matrix is invertible. Let's try it in practice. So I'm going to do a 3 by 3 example. I'm going to take my matrix A to be the matrix 1, 2. Sorry, what did I really want? 2, 1, 0, 1, 2, 1, 0, 1, 1, like this. So we're going to form the super augmented matrix and then do row operations until we get to row reduced echelon form. So our initial matrix is A 0, 1, 1, followed by the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. And we've got to do row operations to this until we reach row reduced echelon form. So the first thing that we might do is say, well, I quite like that row that begins with a 1 to be at the top, so I'm going to swap 2 rows. So row 2 is going to swap with row 1. So I'll get, in this case, we're changing 2 rows, and we'll end up with 1, 2, 1, 0, 1, 0. We're changing the second row because we're swapping it, so 2, 1, 0, 1, 0, 0, and we're leaving the bottom row alone, so 0, 1, 1. And 0, 0, 1. Okay, now we have a leading entry in row 1 which is equal to 1, which we're happy about, but the first column which contains a leading entry is not all zeros, so I need to eliminate the 2 in position 2, 1 of this matrix by subtracting a multiple of row 1 from row 2. So row 2 is going to go to row 2 minus 2 times row 1, and we'll see where that takes us. So row 1 will stay the same. We'll have 1, 2, 1, and then 0, 1, 0. Row 2 is going to change, so we're subtracting 2 times row 1. So we'll get a 0, and then a minus 1. No, sorry, we'll get a minus 3. We're subtracting 2 times 2, and then a minus 2. And then on the other side, we'll get a 1, and a minus 2, and a 0. Then the final row will stay the same again, so 0, 1, 1, and then 0, 0, 1. Okay, so we would now like to eliminate things in the second column. So you can see there's a leading entry in row 3, which is 1. So rather than do the swap, I think I'll just do the elimination right now. I'm going to use row 3 to eliminate non-zero entries in the same in column 2. Using the bottom row. So we'll send row 2 to row 2 plus 3 times row 3. Okay, so what do we get when we do this? Let's start a new line. Row 1 won't change. And in row 2, that's where things will start to change. So we'll get a 0, we'll get another 0, and we'll get a 1, and then a 1, minus 2, and a 3, and then the bottom row will stay the same. Okay, let's eliminate the 2 in position 1, 2. So we're going to have row 1 going to row 1 minus 2, row 3. So we'll have row 1 becoming 1 and then a 0, and then I'm taking off 2 lots, so I'll get a minus 1 and then a 0, 1, minus 2, and row 2 will stay the same. It's 0, 0, 1, and 1, minus 2, 3, and row 3 will stay the same, so it's 0, 1, 1, and 0, 0, 1. Okay. And we are nearly done. We've got some problems with column 3, and there's the nice leading entry in row 2, but the other entries in that column are not 0 yet, so we need to do some elimination in column 3. So let's eliminate the minus 1 in position 1, 3 by sending row 1 to row 1 plus row 2. So where does that take us? Row 1's going to change, and it's going to go to 1, 0, 0. And then we're adding row 2, so we'll get a 1, and then minus 1, and then 1. And the other 2 rows will stay the same. Okay, so we still have some elimination to do in column 3. We've got to eliminate the 1 in position 3, 3. So we're going to subtract row 2 from row 3. So row 3 will become row 3 minus row 2. So where does this take us? Rows 1 and 2 will stay the same. So I'll have 1, 0, 0, 0, 0, 1, and 1, minus 1, 1, and 1, minus 2, 3. And then the third row will become 0, 1, 0 there, and I'll get a minus 1 here, and a 2 here, and a minus 2 just here. So finally, I just need to get my columns in, my rows into the right order. So we need to swap rows 2 and 3 and see where this takes us. So rows 2 and 3 get swapped, and we end up with 1, 0, 0, and then 1, minus 1, 1. Row 1 doesn't change. Rows 2 and 3 do change, and we get 0, 1, 0, 1, minus 1, 2, minus 2, and then 0, 0, 1, 1, minus 2, 3. And you can now see that we're done. We have reached row reduced echelon form, and we found that the first 3 columns make up the identity matrix. So A is invertible because this bit is the 3 by 3 identity, and A inverse is the right-hand part of the matrix, which is 1, minus 1, 1, minus 1, 2, minus 2, and then 1, minus 2, 3. Okay, now I'm not guaranteeing that I've not made any arithmetic errors doing this, so you should check this. But the nice thing about this kind of calculation is that it's very easy to check. So people who've grown not to trust my arithmetic, or their own arithmetic, should check by multiplying A and what I'm claiming is A inverse. So you can check whether or not you really do get the identity, and if you do, our calculation worked.